Well, in this new playlist, I want to focus on dialogue systems. And in each lecture, I want to focus on one or two or three articles in this research area. And so I like dialogue system research because it is intersection of three areas: deep learning. You can watch my playlist about deep learning, those LSTM models, GRU models that we need them very much. Also, NLP and reinforcement learning. We use this for example, policy optimization in dialogue systems. And there are great researchers in this field. And so there are two types of dialogue systems, let's say. There are two types of problems, let's say: open domain or task-oriented. In open domain, there is no exact role. We talk about everything. We don't want to achieve anything. We have infinite space of inputs and outputs. If you remember the decoder section of encoder decoder sequence models, for example, this is a bi-LSTM, this is an LSTM, and you use beam search, and because the space of words is so big, you have some problems, and that's why you create new versions of beam search. This is the same problem here. Because it is infinite space of inputs and outputs, you don't know what in word generation, in language modeling, we don't know how to reduce this space. This is this big space. So that's why this is a big problem in open domain. But in task-oriented, the problem is still hard, still really hard, but the amount of the trajectories that could be generated in task-oriented dialogue are less in comparison to open domain. And because we have an exact goals and finite space of inputs and outputs, and finishing a dialogue as soon as possible. And so this determines the reward, because if you could answer your customer very quickly, it has high reward. And if you just talk about if you use different sentences that are not relevant to that, it's a bad reward. So it's a punishment, let's say. And you typically see it in Apple Siri or Amazon Alexa and those things. So the solution is sometimes merging these two worlds of task-oriented and open domain. So there are some articles for task-oriented, combining them. It's a fusion of task-oriented and open domain. And sometimes, like this article, they just see it at a hierarchical level. You see that everything is like task, but at a different level. So the dialogue management is really complex. We have different modules, like the dialogue system, even the dialogue management has two subsystems: dialogue state tracking and the dialogue policy. So this is the standard way, but this dialogue system could be changed. I mean, each person implements it differently. Also, the modules, I've seen some people use 7 or 8 modules in their frameworks. So it's still an open domain. And so some people use totally end-to-end. And so the way they train their models is different from one article to another article. So the dialogue state tracking, this is just one approach that people use: domain and intent and slot, but you can also go beyond this slot level. You don't even need to use this methodology, but it's very common to use. So we go from domain, and then you go to the intent. This is the intent, and you go down to the slot filling. So you go from very abstract things to very concrete things. And the dialogue state tracking is like this. You have a dialogue, you say, for example, I would like to book a room for 2 nights, and then it states the track. So 2 rooms for 2 people and those things. But the thing that I want to share, I want to say here, focus is that it also understands something that is related to previous turns. Let's say, there same day it should understand. It should remember the previous utterances so that it could be related. So it's like co-reference, and that's why the problem is really hard. And there are lots of data sets for dialogue state tracking. But today I want to focus on dialogue policy because I really like reinforcement learning. I also like graphical models, so I can see how can we use those paradigms, let's say, for this challenge of dialogue systems. And so we, in real-world applications, using explicit user feedback as the reward signal is often unreliable and costly to collect. So the solution is that the dialogue policy is jointly trained alongside the reward model via active learning with a Gaussian process model. So the dialogue success can be determined. So the dialogue success can be determined from the subjective user ratings or an objective measure based on whether or not the pre-specified task was completed. Because if it is completed, it has a high reward, as I said, those things. So in this article, we model this dialogue representation and we feed it for the reward model. And I will explain how. So a typical approach to defining the reward function is in task-oriented dialogue system is to apply a small per turn penalty to encourage short dialogues. If we want to answer the question of the customer as short as possible, so we give high reward to short dialogues because they can answer the customer as quick as possible. And we give large positive reward to the end of each successful interaction. So there are 3 main parts of this model. We have a dialogue policy, we have a dialogue embedding function, and so it creates this representation D and an active reward. So when each dialogue ends, a set of turn level features FT, these are FT that are given, they are extracted and fed into the embedding function, and to obtain a fixed dimension dialogue representation D. That serves as input space of the reward model. So once we have this D, we can talk about the reward model, how to model it, and we model it using this Gaussian process because it is non-parametric and helps us a lot, especially to understand in uncertainty representation, because it could have very different trajectories, and it can represent the. I've used this Gaussian process in my article for Bayesian approach to graph partitioning, and that's why I really like this Gaussian model. So the quality of each dialogue is defined by its cumulative reward. Because we want to add all of these, I will explain later. You want to add all of them, so it's cumulative. And each dialogue turns incurs a small negative reward and a final reward of 0 or 20, depending on the estimate of task success. So in order to model user feedback over dialogue, for varying length, an embedding function is used. So inspired by this article, that for this reason, they use the same idea. So because in language machine translation, they have done this before in this article. So this is the source of inspiration, because they wanted to model user feedback over dialogues, because we want to map each dialogue into fixed dimensional continuous space. And this is like the problem of machine translation, that the length of different sentences is different. That's why you have this is another way to handle this challenge, but this article uses this embedding. So that is the motivation for using this embedding. We want to represent this complex dialogue into a fixed dimensional vector. And we use it with LSTM, and they use it bidirectional. This is forward, this is backward. And then they concatenate it becomes HT, and then they average that. Remember, this is the average of vectors, so it becomes D becomes vector. So D is like this. The first entry, second entry, that's why we can model this Gaussian process at different entries of this hidden state, that we have taken average. And so H of T is the concatenation of forward and backward hidden states of your bidirectional LSTM model. And the training is easy because it's just like autoencoder. The input is like the output, so it should be minimized. So once we have done that, once we have done that and we know the answer, and we got the parameters, then we are ready to use the reward learning, because now we have the D. Because now we have calculated D, and now we want to know the next step, which is to model reward model to know what is the signal that you are giving to dialog policy in order to generate some episodic features. So here we propose modeling dialog success as a Gaussian process. This involves estimating the probability of Y given your D, which is your dialog representation, and of course capital D, it contains the pool of all of these dialogues, and also for the previous dialogues as well. So we pose this as a classification problem where the rating is a binary observation that defines the failure or success. Does it achieve the goal? I mean, could it be ended successfully? Because if it ends successfully, it means that the customer is agreed with the chatbot. I mean, the chatbot could have answered the query of the customer successfully. It has talked about the relevant answers, and the conversation is ended successfully. Otherwise, if, for example, something happens and the chatbot keeps repeating cyclic things that are even irrelevant, and those things, that is failure. So it's either failure or success. Success is 1, failure is -1. And we model it using the Gaussian process prior. And using prior, you estimate the posterior, and so you have some hyperparameters to tune like any other Gaussian process method. So there, you can also estimate the uncertainty, and that's the point behind the Gaussian using Gaussian process. You see, sometimes The uncertainty is low, sometimes it's really high. And what is important, we want to know what is the probability of success. What is the probability? So the probability is between 0 and 1. We can understand the probability of success. And we use this as a reward function in order to be used for dialogue policy to generate episodic features. So the hyperparameters, as I said, can be adequately optimized by maximizing the marginal likelihood using a gradient-based method. But phi is, as I said, it is accumulative. It's not Gaussian. So the resulting posterior is analytically intractable. So we approximate it. So we use expectation propagation. And I will explain about LoVA in the third lecture. In the next lecture, I will talk about where is that? The Zhao article, maybe here. First, I will talk about Zhao article in the next lecture, and then because it is a prerequisite to this article, to see the historical evolution of these ideas. And of course, this is a good thesis. And I will also talk about in lecture 4, I guess, this article from Amazon Alexa AI in lecture 4. And this is a successful company, Rasa, that has leveraged these dialogue systems in real world, in banking. The customer says, for example, something, and the chatbot replies that your recent transactions are this, and the customer says, how much money did I spend on food? The chatbot said, you spent this on food, and then how much money did I transfer to Max? You have transferred money to multiple people with the name Max. Which Max do you mean? And says, I mean the first one. When it says the first one, it should automatically remember all of these previous terms. So that's why long-term dependencies in dialogue are really important. It's like coreference resolution, that you need to know the previous sentences and all of those things. And that's why it's really a challenge.